Welcome back to the deep dive. Um, Today, let's start with a scenario that I think is, well, I'm pretty sure it's going to feel painfully familiar to you.
Oh boy.
Yeah, so you've had a long day, right? You walk into the kitchen, you open the fridge, and you just sort of stare.
Ah, yes, the abyss.
Exactly, the abyss of leftovers. And you stand there for what feels like um, maybe 5 whole minutes debating the nutritional value of leftover pizza versus making a salad,
Right.
calculating the exact expiration date of that yogurt in the back,
Yeah.
weighing the pros and cons of turning on the microwave because, I mean, it just seems like so much effort.
It's total analysis paralysis.
Yeah.
You're applying this high-level strategic planning to a decision that honestly just does not matter at all.
Right. And then paradoxically, maybe an hour later, you're sitting on the couch booking a flight or buying some expensive gadget online.
And you just click purchase.
You just do it. You don't even
Yeah.
read the return policy.
It's the classic human condition, really. We are terrible at allocating our brain power. We totally overthink the small stuff, and we underthink the big stuff.
Which is exactly what Daniel Kahneman described in his famous framework, thinking fast and slow. We have the system 1, which is fast and intuitive.
Almost reflex-based.
Yeah, reflex-based thinking.
Yeah.
And then system 2, which is the slow, deliberate, heavy-duty reasoning. We humans have both gears, even if we grind them occasionally.
We do. We switch back and forth constantly all day long.
But here is the thing that really sets the stage for today's deep dive. Until very recently, artificial intelligence couldn't really do that.
Right, it didn't have a gearbox.
Exactly. It was either stuck in first gear or fourth gear with absolutely nothing in between.
That's a perfect way to frame it, actually. AI has historically been very rigid in how it processes information.
But that changes today.
Yeah.
We are unpacking a fascinating new paper, and it's titled Think Fast and Slow Step-Level Cognitive Depth Adaptation for LLM Agents.
Quite a mouthful.
It is, but the researchers have basically proposed a framework called CogRouter. And I want to spoil the ending right now for you because the results are honestly shocking.
They really are. They took a relatively small AI model, not one of those massive trillion-parameter beasts, and gave it this ability to switch gears.
And the result? It outperformed the absolute giants. It beat GPT-4o.
Yeah.
It beat OpenAI's new reasoning model o3. And this is the part that just blows my mind. It did it while using 62% fewer tokens.
Which means it used 62% less computing power. It's smarter, faster, and radically more efficient.
So our mission today is to figure out how. We really need to look under the hood of CogRouter. How does an AI learn to know when to think hard and when to just chill out?
Right.
But before we get to the solution, let's unpack the problem. Why is the current setup for AI agents so inefficient?
Well, first, I think we need to define what we mean by an agent. We aren't just talking about a simple chatbot where you ask a question and it gives an answer.
Like ChatGPT.
Right. An agent is designed to complete multi-step tasks, long horizon tasks.
Give us a concrete example of that.
Sure. Imagine you have a digital assistant and you tell it to plan a travel itinerary for a weekend in Paris. That isn't one task. It's really 100 small tasks chained together.
Right, because it has to do step A, then step B.
Exactly. Step 1, check flights. Step 2, compare prices. Step 3, check hotel availability. Step 4, map the distance between the hotel and the Eiffel Tower.
So chain of actions.
And in that chain, not every step is difficult.
You got
Checking
it.
the flight price is just a data retrieval task. It's simple.
Right.
But optimizing the schedule to fit 3 different museums into one single afternoon, that requires strategic reasoning.
Okay, I see where this is going. In the old world, or I guess the current world, you have to choose your AI model before you even start the task.
Precisely. You have a binary choice. Option A, you use a fast model. Think of a standard LLM. It's cheap, it's quick, but it operates largely on reflex.
So if you ask it to do the complex scheduling, it might just mess up.
Yeah, it might just hallucinate a time that doesn't exist because it didn't stop to calculate the travel distance between the museums.
So that's the system 1 approach?
Yeah.
Fast, but very error-prone on the complex stuff.
Right. Then you have option B, the reasoning models.
The heavy hitters.
Exactly like the O1 or O3 series. These models utilize chain-of-thought processing. So before they answer, they actually pause, they generate a hidden internal monologue, they reason through the problem, and only then do they act.
Which sounds great. I mean, why not just use that for everything?
Because they use that heavy process for everything, even when it's totally unnecessary.
Oh, I see.
If you ask a reasoning model to tell me the capital of France, it might spend valuable computing resources analyzing the history of geopolitics and the definition of a capital city before finally spitting out Paris.
Wow, so it's the computational equivalent of hiring a PhD in mathematics to calculate the tip on a dinner bill.
That is exactly it. They'll get it right, but they might spend 20 minutes driving the formula first. It's incredibly wasteful.
And in the world of AI, waste equals money and latency.
Exactly.
So the goal is dynamic adaptation. We need an agent that isn't just smart or fast, but one that actually adapts its cognitive depth depending on the specific step it's facing in that moment.
Correct. And the authors of this paper didn't just invent this concept out of thin air. They grounded their framework in human psychology.
Yeah, I saw that. Specifically something called ACTR theory.
Yes, ACTR.
That stands for Adaptive Control of Thought Rational Right. It's a cognitive architecture used to model how humans think.
It is. It essentially posits that human cognition isn't a monolith. We have different modules or levels of processing.
Right.
The researchers adapted this to define 4 specific cognitive levels for their AI.
Let's walk through these levels because I think this hierarchy is really the core of the machine here. I'm looking at figure 2A from the source material, and it lays them out almost like a ladder.
Yeah, a ladder is a good way to look at it.
Level 1 is at the very bottom.
Level 1 is the intuitive response. The pathway is simply situation leads directly to response.
So no thinking time at all, just pure action.
0 internal monologue. It's a reflex.
Like grabbing a falling coffee cup.
Exactly. In the context of an AI agent effectively navigating a computer, this might be clicking the next button. You don't need to ponder the existential meaning of the button. You just click it.
Okay, so that's the baseline. Then we step up to level 2.
Level 2 is standard processing. It's a bit more than a reflex. It might involve retrieving a specific rule or a fact from memory.
So the path is still direct, but the processing is just slightly heavier.
Right.
Okay. Then we hit level 3, and this is where I feel like the AI starts to actually act like a person.
Level 3 involves reflection. The pathway changes here. It becomes situation, then reflection, then response.
Oh, so the agent actually stops.
It does. It generates a brief internal thought to evaluate its current state.
Can you give us an example of what that internal thought actually looks like?
Sure. Let's say the agent is trying to solve a puzzle and it hits a wall. A level 3 thought might be, wait, the last action didn't work. Is there a constraint I missed? Let me reread the instructions.
It's a sanity check.
Exactly. It's checking its own work.
I love that. It's the wait a minute moment we all have. And then finally we have level 4, the big brain mode.
Level 4 is strategic planning. Situation, then reflection, then simulation, then response.
Simulation.
Yes. Here, the agent isn't just checking the present, it's actively simulating the future. It thinks if I do action A, then B will happen, which might block C. But if I do X instead...
It's playing chess.
It is playing chess with the task. It simulates the outcome before committing to the real-world action. And as you can guess, this is the most expensive, most powerful mode.
So we have a gearbox. Reflex, standard reflection, and simulation. That sounds amazing in theory. But here is the million-dollar question, and really the hardest part of this whole engineering challenge.
How does it know when to shift gears?
Exactly. How does the AI know which gear to use? Because you don't want a human standing over the AI's shoulder shouting, shift up or shift down.
No, you don't. The AI has to feel the road itself.
And that is the core innovation of CogRouter. It's the router part of the name. It uses a really clever 2-stage training process to learn this judgment.
Right. And the 2 stages are very distinct from each other. The first stage is called CoSFT.
Which stands for Cognition-aware supervised fine-tuning.
Yes.
That is a mouthful.
Yeah.
Let's unpack it. What happens in stage 1?
Think of stage 1 as skill acquisition. You can't expect an AI to decide when to use level 4 thinking if it doesn't actually know how to perform level 4 thinking in the first place.
Right. It's like me trying to decide when to use a specific karate move. I don't know karate, so the decision is entirely irrelevant.
Exactly. So in this stage, they take the base model, and remember, this is Qwen 2.5, a relatively small 7 billion parameter model, and they feed it a balanced diet of examples.
Okay.
They use expert annotations to show it, here is a problem solved perfectly with a reflex. Here is a problem solved perfectly with deep simulation.
So they are teaching it the moves. The paper calls it instilling stable, level-specific patterns.
Correct. By the end of stage 1, the model is capable of thinking at all 4 levels. It has the range.
But like your karate example, it doesn't necessarily have the wisdom to know when to strike.
Right? It knows how to simulate the future, but it might try to simulate the future when someone just asks, what time is it?
Which would be a huge waste of time.
Exactly. And that brings us to stage 2, COPO, or Cognition-aware policy optimization.
This is where the magic happens. This is where it learns the policy of when to actually switch those gears.
Yes.
And this uses reinforcement learning,
Yes.
RL.
It does, but with a critical twist. Usually in reinforcement learning, the AI is rewarded simply for getting the right answer. Did you solve the math problem? Yes. Okay, here is a reward.
But COPO is different.
COPO is much more subtle. It uses a mechanism called confidence-aware advantage reweighting.
Confidence-aware. So it doesn't just look at success.
No, it looks at the relationship between confidence and cost.
Explain that. How does it balance those two things?
Well, the system defines the appropriate cognitive depth as the level that maximizes the confidence of the resulting action. So let's say the model faces a simple problem, like pick up the apple. It tries to use level 1, the reflex. It succeeds, and its internal confidence score is high. It's 99% sure it did the right thing.
The system says, good job.
It says, great job, you solved it, and you used the cheapest possible method, maximum reward.
Now, what happens if it tries to use level 4 strategic planning on that exact same simple apple problem?
It might still solve the problem. It might successfully pick up the apple after writing a 10-page dissertation on gravity and friction.
Right.
But the system looks at that and says, okay, you got the right answer, but you burned 1,000 tokens to do it. That was incredibly wasteful.
So it actually penalizes the model,
Right.
or at least gives it a smaller reward for overthinking.
Exactly. It effectively teaches the AI to find the minimum effective dose of cognition.
The minimum effective dose, I like that.
If you can nail it with a reflex, do it. But, and this is key, if you try to use a reflex on a hard problem and you fail or your confidence is super low,
And you get punished for being lazy.
right, then the system says, you should have thought harder. You needed level 3 or 4 there.
This is fascinating because it totally mimics how we learn as humans.
Yeah.
If I rush a complex decision and mess it up, I learn to slow down next time.
Yes.
But if I spend 3 hours deciding what sandwich to eat, I realize I just wasted my entire lunch break.
Precisely. It's a continuous efficiency optimization loop. The diagram in Figure 2C shows these loops of expansion and reweighting.
Right. I'm looking at that now.
The model generates multiple trajectories, different ways of thinking about the problem, and the training algorithm reinforces the one that strikes the absolute best balance.
Now, this brings us to a really critical comparison in the paper. Because CogRouter isn't the only attempt to use reinforcement learning to make AI smarter, right?
No, definitely not. The paper mentions other methods like GRPO and GGPO.
These are other state-of-the-art optimization strategies.
They are.
But when the researchers compared CogRouter to those other methods, they saw something really specific happen with the others. They called it the collapse.
Yes, the mode collapse. If you look at the bar charts in Figure 3, it is visually very stark.
The CogRouter chart is like a rainbow.
Exactly. It uses level 1 about 20% of the time, level 2 for 30%, and so on. It's a healthy adaptive mix.
And the other guys.
The charts for GRPO and GGPO are just solid blocks of gray. They collapse almost entirely into level 4 thinking.
Why does that happen? If they are trying to optimize, why do they end up doing the most expensive thing constantly?
Because they lack that confidence-aware penalty for cost that we just talked about.
Oh.
In a standard reinforcement learning setup, the safest bet is always to think more. Generally speaking, thinking longer increases the probability of being right.
So the model learns a very simple heuristic.
Right. It learns every time I think for a long time, I get a cookie. Therefore, I'll always think for a long time.
It basically creates a neurotic AI.
Yes.
This reminds me of the tuxedo at the gym analogy we were talking about before the show.
So please share that with the listeners. It's perfect.
Okay, so it's like deciding that because a tuxedo makes you look really good at a wedding, you should just wear it to the gym.
Right.
I mean, technically you're clothed. Technically you can still lift weights, but you look completely ridiculous. You're overheating and you're ruining a very expensive suit.
It works, but it's wildly inappropriate for the context.
Exactly. Those other models, GRPO and GGPO, are basically wearing tuxedos to every single task.
Every single time.
CogRouter is the only one that actually knows how to put on gym shorts when it's time to sweat and a suit when it's time to negotiate.
And that distinction is what entirely prevents the collapse. CogRouter maintains what we call adaptive allocation.
So we have the theory, we have the training process, and we know why the other methods fail. But let's get to the scoreboard. Does this actually win games?
It does. Section 5 of the paper covers the results on ALF World and Science World.
And just to set the scene for you listening, These are not easy benchmarks. These are complex, text-based simulation environments.
Right. In ALF world, the agent is placed in a virtual house and given a command like, find a clean mug, heat some water, and make tea.
Which implies a lot. You have to find the mug. Is it dirty? If it is, you have to wash it. Where is the sink? Where is the microwave?
Exactly. If the agent misses a step, or if it hallucinates an object that isn't actually there or gets stuck in a repetitive loop, it fails the whole task.
And science world involves running literal experiments,
Yeah.
right? Like connecting circuits or boiling chemicals.
Yes, it requires deep causal reasoning.
So how did our efficiently lazy CogRouter perform on these? Remember, this is running on a small 7 billion parameter model.
The results are honestly humiliating for the industry giants. CogRouter achieved an 82.3% success rate across these benchmarks.
Let's put that in context. How did GPT-4o do?
CogRouter beat GPT-4o by a massive margin of 40.3%.
That is absurd. That's not a rounding error. That is a total landslide.
It is, and it beat OpenAI 3, which, remember, is the model specifically designed for deep reasoning, by 18.3%.
Wow. And compared to the other reinforcement learning methods, the ones in the tuxedos.
It beat GRPO by 14%. This is the critical proof point here. More thinking is not always better thinking.
Can we dig into that for a second? Why would thinking more make the model perform worse? I assume it just wastes time. But why would it actually lead to a wrong answer?
Because overthinking introduces noise.
Noise.
Yes. If the task is simple, like open the door, and the model enters a deep simulation about the nature of doors and locks and security, it creates opportunities to hallucinate constraints that don't even exist.
Oh, wow.
It might talk itself into believing the door is locked when it isn't, or that it needs a key it doesn't have.
It effectively gaslights itself.
Exactly. Level 1 intuition is often much more accurate for grounding tasks because it's direct. It just trusts its gut.
And we have to circle back to the efficiency stat because this is the real kicker here. You mentioned it in the intro.
Yes.
62% fewer tokens.
This is what will make every single engineer and CFO sit up and take notice.
Because tokens are money.
Tokens are money and tokens are time. If you are running an AI agent at scale, say a customer service bot handling millions of requests a day, you are paying for every single word that AI thinks.
So if CogRouter cuts the token usage by 62%, it's basically cutting the server bill by 62%.
Roughly, yes. And it's significantly reducing latency. The user gets the answer faster because the AI isn't sitting there pondering the meaning of life when you just asked for a simple refund status.
It's rare in tech that you get the holy trinity. Usually you have to pick two: better, faster, or cheaper.
But CogRouter actually delivers all three. You get better success rates, faster convergence during training, and much cheaper inference costs.
Speaking of training, figure 4 in the paper shows the learning curves. What did you see there?
That was another huge validation of the method. COPO achieves faster convergence to higher success rates.
Meaning it learns quicker.
Exactly. Because the model isn't wasting time exploring complex, expensive solutions for simple problems, it zeroes in on the correct policy much quicker than the other methods. It learns fast because it learns efficiently.
So zooming out to the big picture here, what does this signal for the future of AI development? We've spent the last 2 years absolutely obsessed with scale, bigger models, more parameters, more compute.
Right.
Does CogRouter suggest a different path?
It firmly points toward adaptive intelligence. We are moving away from the era of pure brute force.
Right.
Think about the human brain for a second. It uses about 20 watts of power. A supercomputer uses megawatts.
Right.
Why are we so incredibly efficient?
Because we are lazy.
Well, cognitive scientists call it being cognitive misers.
Cognitive miser.
Yes, we don't use our full brain power unless we absolutely have to. We coast on intuition for 90% of our day.
And that's a feature, not a bug.
It is absolutely a feature. It preserves our energy for when it really matters. For AI to become truly ubiquitous, to be in our glasses, our home robots, our phones, it cannot run at maximum RPM 100% of the time.
It would drain the battery in 5 minutes.
Exactly. It needs to coast when the road is flat and rev the engine only when there's a steep hill.
And CogRouter is the first major proof that this human-like economy actually results in superior performance.
It validates the idea that true intelligence isn't just about raw processing power, it's about discernment.
Knowing when to think.
Knowing when to think is just as important, if not more important, than knowing how to think.
It's the transition from hard work to smart work.
Literally.
So as we wrap up this deep dive, we've seen that CogRouter uses a gearbox of 4 cognitive levels. It trains using a clever two-stage process that rewards confidence and punishes waste.
Right.
It completely avoids the trap of overthinking that plagues other models, and it delivers better results with a fraction of the cost.
That is a very solid summary.
Here's a thought to leave you with.
Yeah.
We often look at AI and worry about it becoming super intelligent in a way that is just totally alien to us, calculating a million possibilities in a microsecond.
Yeah, the sci-fi fear.
But CogRouter suggests the path forward is actually to make AI, well, a little bit lazier, or at least more selective.
Efficiently lazy.
Exactly. If AI is now learning to skip deep thought when it's not needed, just like we do, does that actually make it more human than the supercomputers that calculate everything?
That is a profound question. Maybe intelligence isn't about the capacity for infinite thought, but the wisdom to know exactly when to stop thinking.
Are we coding our own laziness into the machines? And is that actually the secret to true intelligence? Something to mull over the next time you are staring at the fridge, paralyzed by the choice of lunch.
Just grab the sandwich and save the tokens.
You're not being indecisive, you just have a misaligned cognitive policy. You need a little COPO training.
Exactly.
Thanks for joining us on this deep dive into CogRouter. We'll catch you on the next one.